Hey, Margaret.
So,
Recording is on.
Oh, boy.
Hey again, Margaret. We lost you for a while there.
I turned my video off on purpose.
That's why we lost it. Now we got your hand. Hey, Kira. Kira, are you doing better now that you haven't been away for a week on Thanksgiving break?
Pardon?
I'm checking to see how you're doing.
I'm alright, thanks. Do you have a microphone on that's repeating everything?
Yep. Let's see if we can figure out what's going on with that. Can people hear me? Does that stop the problem? All right. It looks like maybe I had some speakers going on through my computer there. Thanks for checking on that. Hi, Summer. Welcome to class. Hi, Marcel. Welcome to class. I appreciate you guys getting here early. You guys are great about that. Thank you. Did you guys see what I mean about this being a tough unit when you got to the last few sections and then saw some of the homework problems? Or do people think, this stuff is easy cheesy?
More like I need more practice with it?
Yeah, it's hard. Yeah, I'm going to see if we can convince everybody to maybe have another class on Monday where we have more chance to go over homework problems and maybe even go over the test, and then maybe take it Tuesday or Wednesday or something. So I'm going to push for a little more time, but we'll see what the class says. I could always overrule them if they said no, right?
That was by far the hardest videos. Those are the hardest videos.
Right. I told you this one ends really tough. Once they throw E2 and E1 at you, and then everybody's competing and fighting, why can't they just get along?
Yeah, I know, right?
I'm trying to memorize that chart, and
I know, right?
Too hard.
Chart's crazy.
it just blends together.
Yeah.
Basis favorite elimination, though. Got that much.
Yes. Yeah, so I don't know how you guys feel, but I'm going to see if I can convince people to maybe have one more class of kind of going over problems and review stuff, and then maybe take the test after that, like Monday or Tuesday or Wednesday, instead of taking it Monday.
Could I not do it Tuesday? Because I have 3 assessments on Tuesday.
You have what?
3 assessments.
Jeez. Yeah, I mean, I'm not, like, it could be Tuesday, Wednesday, or Thursday. I don't know. You know. Thursday will be kind of an exam review day.
Oh yeah, sorry. How did the exams for this working? That was amazing.
For us?
Yeah.
I think you guys are going to take it Wednesday because that's your conflict day. So like Tuesday would be math, Wednesday would be this, and Thursday would be BC Calc, BC Physics.
I might have to take it earlier, Mr. Walker, because
Okay.
I'm leaving school early.
Which you're,
I am
leaving.
Exactly. 18.
Oh, you are.
Oh, Malaysia.
But when are you taking math?
I have to take it really early.
Oh, math?
Yeah.
Wow. All right, so math is probably Tuesday with the class. So then do you have BC Physics?
Yeah.
And that's what, you got to take that
I have
early?
to talk to Mr. Emerson because I might have to start taking them over the weekend.
I just waved Mr. Kornheiser and he just goes, make sure Young Young doesn't fall asleep.
Nice. Wait, Mr. Kornheiser?
Yeah. Well, I was telling him today how Young Young falls asleep constantly, but then I told him about
is aware of my
organic chem specifically.
Organic should be sold as a sleep aid.
Without the fast-forwarded random music bits.
Right? Yeah, without that. We take out all that and any cheering or loud screaming by crazy presenters.
I have a what's it called
The first
3
30
o'clock dismissal for
The first 30
that one
seconds that I with the boxing thing, I just couldn't stop laughing.
Oh, really?
Here on this corner, we got 150 pounds.
No, it's probably AMUs, right?
AMUs. The fact that you put the time and effort to say AMUs, I was like, that's worth it.
It takes a while to find everything. Like, you got to get the right sounds for the fighting song. It's actually fun making the videos. It takes a lot of time, but super fun. Hey, Keith.
What's up?
How much, man? How about you?
All right.
So we got about a minute till class starts. I was talking to a few people as they were coming in. How's this unit going for you, Keith? I might try to convince people to use next class Monday instead of being a test day. I think it might be wise for us to use it as a day to do more practice problems and stuff like that instead of taking a test. But how would you feel about that?
Yeah, that sounds like a good idea.
And then we could take the test. Yeah, take whatever you want. Like Tuesday or Wednesday or something like that of next week. That might give people a little better feeling for things.
Yeah, I'm having a pretty easy time with this chapter so far.
Okay. It ends hard, I think. I think the last unit is really difficult. I think I said on it it's the hardest video or the most complicated video of the year or something.
Really? Spoke to you too.
Have you seen the last one, 7.7?
No, I actually didn't. Yeah, I didn't get around to watching that.
Yeah, once you see that one, you'll see why. It's a little
sometime
crazy.
I have to watch it.
Yep. You see the fight one?
I did not.
No, you didn't see the fight one. Falling behind.
Yeah, I know. I've actually fallen behind, but I got it.
Okay. All right. Well, I'm going to start class on time today, even though we don't have Robin or Peter. Those guys, for some reason, seem to come in a little bit later. But that's what it is. So, Peter, Robin. Okay. So again, why don't we make this official? How would people feel if we agreed that next Monday, instead of having our test, we actually made it another live class where we meet at 2:15 Eastern Standard Time? And what it would be is going over more problems. I think there are more chapter problems, more homework problems than we're going to be able to get through today. And we could also potentially go over the answers to the tests from last year. I'm just worried that if, we could finish up today, and then I'm worried you're going to go into the weekend and maybe not have studied enough or practiced enough, and I worry that might make you suffer a little bit in terms of how you do on the test. And if we did that, if we had class on Monday, which I'm proposing, we would then move the test to like Tuesday or Wednesday, and there'd be some flexibility in that. And I realize that maybe for a lot of you, you may have a lot of tests to juggle, so I want to talk to people. And if someone wanted to, someone said, you know what, I could just take the test on Monday and I'd be fine, I'm okay with you doing that, you just have to tell me. But I think I'm going to propose that we have a live class and do a little bit more practice on this unit just to feel good about it. So put your video away, Max. So how would people feel about that? Can I get an actual vote at the start here about how people would feel about my proposal? Summer, how do you feel? That good? Marcel, that's good. And don't be pressured if you don't. All right, Kira, that's a good plan. Margaret, you think that's okay? All right, Keith, you're okay. Yun Hyun?
Yeah, like not Monday, right?
Huh?
Not Monday. Right?
Not taking the test Monday. Ramsey? Max?
Whatever.
All right. Hey, Peter, welcome to class. While you were out, we voted you off the island.
Really?
Bummer, right? We are talking about having class on Monday instead of the test, and maybe bumping the test to either Tuesday or Wednesday, and there'd be some flexibility, like you could take it either Tuesday or Wednesday. Would that work for you?
Yeah, sure.
Okay. And at the end of class, if people decide, I don't think we're going to feel good by the end of class today. I think we're going to need a little more practice. But if people are and want to get the test out of the way on Monday, even if we meet class, you could do it on your own and just say, look, I want to get it out of the way. I feel good. Or, you know what your week is looking like in terms of other tests. So if you email me, we can work it out. But I'd need that warning like today or tomorrow so I can let your schools know and get the test to them. So just let me know about that. Okay, so let's jump in without much more messing around. So right now, Monday the 8th is turned blue because it says we have a test. I'll go in and change our syllabus to change it back to a live class, to change it to red, and we'll make our test either Tuesday or Wednesday. How do people's week look next week? Can you pull off a Tuesday or Wednesday test? Okay, we got some yeses. Anybody got a problem? Okay, let me know if that is an issue, but we'll try to pull it off then. And so let's just jump in. This slide just shows, again, the reminder that we've got two things, substitution and elimination, going on potentially. So we've seen that slide before. This shows some substitution possibilities. Again, this is just review from going back to the beginning. An iodide can substitute for a bromide. An oxygen can substitute. An OH could substitute for a bromide. An F oxide could substitute. That could happen analogously with sulfurs. It could happen with some carbons. Here are some nucleophiles. Generally, the more negative, the better the nucleophile. Generally, the bigger and squishier the electron cloud, the better the nucleophile. And then we started into section 7.5 last class, and hopefully you've seen the video on it now, and I'll just zoom through. So 3 things that we talk about when SN1 and SN2 are, which is more possible or likely. So you look at the structure of the substrate. Hey, Robin, welcome to class.
Hello, Mr. Walker.
I'll change your name from absent to a little bit late today. Welcome. Robin, make sure you know that we've decided to have live class next Monday and not take the test on Monday and bump it off like for Tuesday or Wednesday. So we did that for absence. You could also look at the properties of the nucleophile. That could determine whether it goes SN2 or SN1, and then finally the nature of the solvent. Just a quick review. The less number of carbon groups around it, so the less R groups, the more likely it is to go SN2, because that nucleophile has to come in, invert the geometry, and cause inversion, and the less hindrance it has, the better off. If you go SN1, the leaving group just plops off, and that forms a carbocation, and that's most stable if it has lots of R groups. That's why there's a reversal there. Okay, let's keep going. The more polarizable nucleophiles tend to favor SN2. More neutral SN1. Nature of the solvent, just quickly, the more polar tends to favor SN1, where it forms that positive cation. I think that's Robin. Yeah. Hey, Robin, you're going to have to mute your mic. Thank you. That's okay.
Sorry.
Good job. No problem. This weird thing about protic and aprotic solvents, if it's protic, it's got a proton on it that can go in and mess with your nucleophile. So if your nucleophile is not as effective, it's less likely to occur. So that would favor SN1, whereas if it's aprotic, it would favor SN2. Again, not to belabor this too much, that's sort of stuff we just kind of have to memorize. Here are some aprotic solvents that I would give you the names, formulas for. And then we did this problem already, and we talked about it, and I think we did this problem, and this is maybe about where we ended our last class, but the first 2 are called protic solvents. I'll just get my pointer out quickly. There's a proton here on methanol that could go away, and there's a proton here or here on formamide that could go away, and that could actually interfere with the nucleophile trying to come in. So it's going to slow the reaction, whereas this last one, the DMF, there's no proton that can go away. This one's tightly bound to this carbon, so it makes it so that it goes much faster in terms of the substitution reaction, because it's not interfering with the nucleophile that's trying to come in and do the reaction. And this, I guess that's the explanation. All right, so we're ready to start 7.6. This is the next to the last unit. In theory, you guys have seen a video on this. So now what we've talked about, we've spent the whole chapter, sections 1.1 through 5, talking about substitution, the nucleophile coming in, the leaving group leaving. Now we're going to go to the bottom part of this, and we're going to look at elimination. So just again to review, and I actually want you guys to really try to visualize this. Here, it's the hydrogen that I'm pointing to that's 1 over from the carbon that has the leaving group that's going to get attacked. And you would be expected to be able to draw electron diagrams like this. So the nucleophile, which is actually a base, can come in and grab the proton. the electrons that were attached to the proton drop down and form the double bond, and then the lone pair, or sorry, the bond that was here, the electrons drop over and go over to the leaving group and make it negative. And I think if you look at test 1, the very first question on the test basically tells you a reaction can happen either by substitution or elimination. And it tells you this is, what comes in and this reacts with this. Show using arrow pointing diagrams the substitution, and show using arrow pointing diagrams the elimination. So I'm likely to probably give a question very, very similar to that on this test. So make sure you know this diagram. For substitution, you're coming in on the carbon that has the leaving group, and that's the attack. And it's actually acting as a nucleophile there. Here, the same group is acting as a base, not a nucleophile, and that's why these two compete, because it can have a double role. So it's going to go after this proton, not that one or that one, or actually I almost said not this one or this one. Why couldn't I have said that? Why can't I say not this one or not this one? Anybody want to try to answer that? Yeah, Margaret?
Because there's no double bond, isn't it just sort of symmetrical? So.
Yeah. All these hydrogens are the same, so whether I try to take the one we're pointing at, or is implied that there's one here and implied that there's one there, they're all the same thing. So, yeah, this is a tetrahedral, and there's no difference in 3 hydrogens. 2 are not shown. So, but this is a hydrogen that goes away. Its electrons drop down here to form the double bond. These electrons sweep over here. That's something to just practice, and I would predict that I'll ask that exact question or very similar to it again. All right, we already know the first question on the test. Woohoo! Okay, let's keep going. And so this just shows this is an elimination. It's called elimination because we're eliminating an H and a Br in the process. And here's the weird thing again. So we talked about substitution in the first 5 units, and they can be SN1 and SN2. Well, of course, elimination can occur as E2 or E1. We've got to make this complicated, right? It can't be simple. The good news is there's some similarities to E1 and to E2 and SN2 and to E1 and SN1. So I will cover them just like I did SN2 and SN1 in that order. I'm going to cover E2 and E1 in that order. So this will look a whole lot like SN2, except it's elimination. So in E2, it's a concerted one-step mechanism, and that was true for SN2 as well. This time, though, instead of the nucleophile coming in, let me point to it, instead of coming in here, this is where the nucleophile would attack and the leaving group would leave if it were acting as a nucleophile. Attack here with inversion of geometry. Instead of doing that, it's going to attack way back here, 1 carbon over, and rip this proton off. Electrons will sweep down and form the double bond, and these electrons will sweep off and your leaving group will go away. Just like in SN2, there are 2 things in the rate determining step, the nucleophile and the substrate. Double the concentration of the nucleophile, double the speed of the reaction, double the concentration of the substrate, double the rate of the reaction. So the rate is dependent on both. Okay, now this little star right here turns out to be incredibly important. And there's some homework problems that talk about this. I mentioned it in the video, and I'll just make sure I say it again here. This has to happen so that all these groups are in one line. They have to be, in this case, the plane of the board. If this were a molecule, they'd have to be cis and trans from one another across, or across a, and we may just have to see it in the geometry, but they'd have to be axial up and axial down from one another in a, say, a cyclohexane ring. They have to be in the same plane. If it's pulled off at all, this won't work. So again, look at this. Notice this hydrogen, this carbon, this leaving group are all in the plane of this board. We can tell that because this group's going back and behind, out in front, over to the right and behind, over to the right and front. But everything that's involved in this process is in the same plane. So they have to be trans to one another. And if you ever see a problem where things are cis, this won't happen. That's a big hint. It can't happen cis. They have to be trans. And in a, especially in a ring, the ring is forcing things to be kind of lined up in this way. We good on that? You may have to stand up if you find yourself getting sleepy. I really do have to patent this stuff. All right, here's the...
No, it's not you. I think it's him.
I think it may be.
How much do you sleep every night? Like
we're going to do a sleep survey.
Do you get your 8 hours?
No,
I see you getting like
8 hours. I get like 6.
Okay. But I mean,
that's not enough.
No, yeah, isn't that enough?
No.
I get 3 on average.
That's not enough, but at least you're staying awake. Yeah.
Can you just say one more time why the nucleophile attacks the H on that carbon and not on the other one?
Yeah, sure, Keith.
I shouldn't.
No, I'm going to try to think if there's a good answer to that.
Why is
the nucleophile attacking in the mechanism? Why is it attacking this hydrogen back here rather than say there are 2 hydrogens right here that it could attack?
Right.
Partly, Keith, it's a great question. Partly it has to do with where the electron is going to drop from. And maybe this whole lineup like this is why it's so important. But if it attacked, say, this hydrogen sitting out here or over here, the electrons would then... It's a problem with the way the electrons have to go. Watch this. Notice how flow is to the right, to the right.
Yeah.
We can't have flow to the left and to the right, because then this carbon is left with, I got electrons leaving me on both sides. That's not fair.
All right, that makes sense.
Thanks. It's a really good question. They have to flow in to account for these going this way out. So this is the only place they can come from for this to work. So I really like it when you guys ask questions. Thank you for that. Let me go back a slide and make sure I didn't jump too far ahead. All right, so yeah, we're right in the middle of talking about this E2 concerted one-step reaction mechanism and them having to be trans to one another. Okay? So this is maybe the only star to really put in your notes to make sure you're clear on. This point can be really important, and you'll see it in lots of homework problems. There's guaranteed to be at least one test question that addresses this fact, that when the elimination occurs, those groups have to be in the same plane. And if one's equatorial up and the other's equatorial down on the other carbon, that won't work. They have to be lined up in a plane.
That works, and the elimination just won't happen, or the reaction won't happen, or it
happens to a much, much, much lower extent.
Okay.
Mostly we'll just say they kind of have to be transferred to work smoothly, let's say.
Okay.
All right. Okay, so again, this is our slow step. Oh, sorry. Now we switch to E1 mechanism, which is analogous to SN1. And remember, the weird thing about it, even though it's E1, it happens in 2 steps. The first step is ripping off the leaving group. So this is just like SN1. The first step was knocking off the leaving group and forming a carbocation. And the next slide will show this, if this were SN1, the next thing that would happen is the nucleophile could come in, from either side. But since it's E1, we're going to be going after this proton. But the next slide will make this more clear. So first step, ripping off the leaving group, and here it is. If we go this way, the nucleophile comes in, and it's substitution. If we pull off this proton right here, it's substitution. Electrons drop down, we form the double bond. So here's the competition for E1. It could go, if it goes the top route, it's actually going SN1. If it goes the bottom route, it's truly going E1. And please believe me, I understand how really confusing this is in terms of you keep yelling out things like SN1 and SN2 and E1 and E2, and it gets crazy. So make sure you take the time to slow it down and make it make sense to you. And just like Keith did a minute ago, he asked a question. Please stop me and ask questions. I always appreciate that. All right. And this is just that mechanism shown again on a separate slide. All right, so that's it for elimination. 2 ways. It can happen as a single concerted step, and that's called E2, where the nucleophile comes in, grabs this H, electrons drop down, lone pair leaves. These groups have to be trans from one another. It happens in 1 step. That's E2. E1, it happens as 2 steps. Let's back up for a second. The first step would be pulling off the leaving group. And then the second step, we have to follow this bottom route, is now the base, the nucleophile acts as a base, pulls off this proton, electrons drop down, and forms the substituted alkene. Kira, is that a question?
Kind of. Is there a way to tilt the conditions to make it one or the other?
Yeah, great question. Yes, and that's what we're going to be talking about next, which actually makes this really super confusing. Yes, depending on how strong the base is, it's more likely to go, one way or another. Super strong bases push for elimination because they attack the proton more, and better nucleophiles make it go the upper route. So a big squishy nucleophile will make more likely for substitution to occur, and a really hard, tight base will make it more likely to go to the bottom. Great question. Okay, this last unit, 7.7, is by far the hardest. The video is long, is difficult, it's confusing, the chapter's confusing. If you even read it, it's confusing. Even when I teach it, I feel like it's confusing. And I look at the chart and find it confusing. So this is just hard. There's no way around it. And I hope that when we get to the questions, those are like good examples of how to make this make sense. So I promise you that I realize this is very difficult. And I think even looking at this chart, it's hard to make it all make sense. But what it's doing is comparing if you have one R group, or if you have two R groups, or if you have three R groups. Clearly, you have to have a leaving group. That's your X, like a chlorine or something that leaves. And again, we could either come in and substitute and do SN1 or SN2, or we could come in and attack the proton off here and have elimination E1 or E2. And what this just does is, in a chart way, is try to say which is more likely if you have one R, two Rs, or three Rs. And the weird, crazy part is in the middle. So you always start from the outsides. And again, we're going to break it down on the slides a little bit. If you have a single R, that's least steric hindrance and more likely to go SN2, very unlikely to go SN1, because if the group pops off, you've just got a single primary carbocation that's not very stable. Similarly, if you have three groups, it's not likely at all to go SN2 because it's too bulky to cause that inversion as the nucleophile tries to attack. Whereas SN1 is much more likely. As soon as the leaving group leaves, the carbocation that forms in that first step is stabilized by the three R groups. And it's also more likely in polar solvents. What gets crazy is once you get into the middle. So it can happen if you've got two. It can go SN1 if it's resonance stabilized because the carbocation is stabilized. E1 and E2, again, it can always go E2, especially with a decent base, no matter what. And again, E2 and E1 and SN1 are going to compete. E2 and SN2 are going to compete. And I hope that the next couple of slides will attempt to make this a little more clear. But again, it's just difficult. So I'm going to move on. And this is, in theory, this is the same thing. This is the way your book did it. And what I did is just try to convert it into something that made sense to my brain. So decide which of these two you like better. This is in our textbook, though, if you want it. Okay. So again, starting out at the ends, like tertiary carbon, so we've got three R groups coming in. This is going to be mostly favored for ripping off the leaving group, so SN1 or E1. It's way too much steric hindrance to go SN2. It can eliminate by either E2 or E1 depending on the basicity. Again, this is what makes this hard, so it's hard to predict which one. Depending on the basicity of the nucleophile and the polarity of the solvent. If the nucleophile is a weak base, SN1 and E1 compete. Using strong bases pushes for more elimination. And again, I hope some of the practice problems will sort of show this. Here's an example. And again, I think real-life examples are always better. And this is where I want you to put your energy on more than anything else. So let's look at this. This is a tertiary alkane. It's got a bromine that's ready to go. And this is super critical. I really want to look at the entering group. This is our nucleophile. And it's important to note, you need to ignore the H. The H is not going to be there, even though it's there now. It's an ethanol. Once this jumps on, the H you have to imagine is gone, and it's the O that's going to come in here and replace the BR. Notice there's an O where there was a BR, an OCC. So that, again, I think that can be confusing to people. This is not a great nucleophile. Can anyone tell me why it's not a great nucleophile? I know this is hard, but Somebody raise your hand and say, well, here's why I think it's not a great nucleophile. Ramsey, I think I saw your hand come up first. Go ahead. Yeah, and also talk to me one more thing. Someone add one more thing about it.
Wait, we didn't hear what he said, or I didn't.
Yeah, sorry. Why? Repeat what you said.
It's not basic, and well, as it says there, and it's also not very polarizable.
It's not very polarizable. It's not very basic. There's one more thing I want to hear about why this is pretty lousy as a nucleophile. Think about that chart of nucleophiles and why they were better as they went down. And then what else was a characteristic about them? Almost all of them were blank.
Neutral.
Negative. Okay? If this were negative, it would be a better nucleophile. And if it were a sulfur negative, it would be a really good nucleophile. Like if this were an carbon-carbon sulfur with a minus charge, it'd be a really good nucleophile. Lots of negativity and lots of squishiness in the electron cloud. This is not such a good nucleophile because it's neutral, and like you said, it's actually kind of hard. It's actually not a good base either.
Because we're ignoring the H.
Please.
We're ignoring the H. Does that mean that it's like kind of like is that?
I don't mean to ignore. I mean to ignore the H in terms of predicting what the product's going to be as a substitution product. Like that H has got to go away for the O to come on there. Is what I'm kind of saying to you.
Yeah.
Also, as Ramsey said, it's not a good base. And to act as a base, it's got to come over here and rip this proton off right here. And this is a horrible base, and that's why we don't get much in terms of elimination. Now, I could also rip this proton off because that's 1 over as well. So if I wanted you to key in on anything, it would be maybe to try to get a sense of that this is not a great nucleophile, that substitution is probably, like SN1 is maybe more likely, especially since we've got an R3 here, SN2 hardly likely at all. Now, what could make us have more elimination products? We can predict. What's the next slide going to show? What would make it? How do we make this so we eliminate more and substitute less? Yeah, Ramsey.
Very strong base.
Use a stronger base. So that's what the next slide should do for us. Where are we? I went too far. All right, here we go. There, one slide away. Now we've ripped the proton off. Now it's a better base, and all of a sudden, instead of getting lots of substitution and little elimination, we get mostly elimination. And now this guy's a super strong base, so it's coming and ripping off this proton very actively, not coming in and substituting much for the bromide by SN1. So being able to know why, and key in why this mostly substitutes and why this mostly eliminates, is kind of where I want you to put your brain power. And if that makes sense to you, or at least you can memorize the thing about bases causing more elimination, that'll be good for you. And that's the kind of things I'll be testing more than all the other stuff that sort of begins this. So let me pause for a second. Are we okay? Even though this is hard? Okay. Let me go on to the next slide. So that was tertiary. Now we're going to go to primary haloalkanes. Now there's only a single R group on, 2 hydrogens and a leaving group. Okay, so we could either go SN2, again, because we're going to cause that inversion, or we could go E2. A primary carbocation is too unstable to go either SN2 or SN1, sorry, I can't speak, or E1, because that would involve ripping off that leaving group, and then the carbocation wouldn't be stabilized. All right, so SN2 will go if you have strong nucleophiles, as long as they're weak bases, and this is a great example. Like if you could remember that this guy's a really good nucleophile, it's got all the nice characteristics. Let me point to the S. Nice, juicy, negative charge, big sulfur atom, bigger than that tiny oxygen we saw in the last one. So this is a super good nucleophile. And in fact, when it comes up against this, it only substitutes, or really you don't get much elimination at all. And again, I'm hoping that you're getting better about feeling what a product like this would look like. Your leaving group leaves, and your entering group, your nucleophile, just pops on where it was. So I'm hoping that, oh yeah, I get that. I could say what the product of that reaction was if this were left blank. I'm hoping that that's what you feel like. So if we move to an ethoxide, it's a worse nucleophile, and this is coming up on the next slide, and it's a stronger base, so we up the amount of elimination. So let's go to that. Now, this is a better nucleophile at least than the methanol we had, where it was an OH. So we still get a significant amount of substitution, but now we're starting to get more elimination because this thing is also basic. So it starts to compete. It starts going after, tell me which hydrogen I should point to. Should I stop here, 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 or here? Which one's going to go away? 1, 2, 3, or 4? Which hydrogen off which carbon? 1, 2, 3, or 4?
3.
3 is the correct answer. Yeah, these are the hydrogens have to leave from here. The electron's going to drop down and form a double bond right here, and the leaving group's going to leave there. Again, I know this is hard. That's why I'm trying to repeat things, but it's the hydrogen's going to come away from this carbon here if we do elimination. If we do substitution, it just comes in and steals that away and replaces the bromide. All right, so now I think the next slide is going to say, what would we do to make even more elimination? What's different in this slide and that one is we have
different whatever.
Oh yeah. So we make this nucleophile, instead of just having a line of straight carbons back here, now we make this really big and bulky. This is called a T-butyl group. Basically, you have 3 carbons sitting out here. It makes it really big and bulky. So substitution is much harder because remember, in substitution, the nucleophile has to come in like this on this side if this were drawn molecularly as the bromine leaves. And unfortunately, this group is so big that it blocks a lot of the substitution. So this is going to be more acting like a base. The other thing is this actually turns out to be a stronger base. Those R groups donate in electrons, and it makes this more likely to, it just makes that a more stable compound and makes it a better base. It's more willing to grab hold of a proton. So in this case, we get a little more elimination if we make this group big and fat here. All right, again, this is difficult stuff. Let me go on to the next slide. Now here's where it all goes crazy. When you've got a secondary haloalkane, it's almost like all bets are off. For primary, at least it leads one certain way, and for tertiary, at least leads one certain way. For secondary, it could do SN2 or E2, SN1 or E1, and maybe that's good. It's so hard to predict. Maybe we won't be asked to predict. That's maybe the good news of it. Super strong nucleophiles that are weak bases are going to tend to favor SN2. So here's another good example of a super good nucleophile, and here's a new one for us, at least in terms of this slide today, the cyanide ion. So these guys will principally go SN2 product, even though it's a secondary carbon. So what pushed it that way? A really good nucleophile. Anything else will be a lot of mixtures of stuff. So in the next slide, now we're moving back to, oh my God, horrible, horrible nucleophile. This is a terrible nucleophile. So again, weak nucleophiles such as ethanol favor SN1, but there is some competition with E1. So you can get some elimination going on here. I'm actually surprised in some ways that this much substitution occurs, but this is such a horrible base as well. I think Ramsey said at the beginning of this section, it doesn't cause much elimination. It's just a really bad base. All right, let's go to the next slide. And now this is a pretty kicker base. Yes, sir, Peter.
On the previous slide, why isn't SN2 also formed?
All right, let me think about that for a second. Yeah, I don't think there's a good answer to your question. Here's a... Maybe because for SN, I think you'd have a legitimate point that there could be some SN2, and I wonder how much this is just. Once you get the product, once you get the substitution product, you actually can't tell if it happened by SN1 or SN2 unless you go back and do some kinetic studies. So I actually think you have a legitimate point there, and I wouldn't expect you to necessarily think, oh, that had to have formed by SN1 versus SN2. So I don't have a good answer to your question. Keith?
Actually had a...
So SN1 and SN2 result in the same product?
Yes.
Okay.
So you wouldn't know looking at the product which is one. It's just the mechanism by which you get there, either 2 steps or 1 step. Peter, I think you had a follow-up.
Yeah. So in SN2, the rate of the reaction is affected by the concentration of the nucleophile and the concentration of the product, the substrate. But in SN1, the slow step is only how fast it leaves. So if the strength of the nucleophile changes, that wouldn't really affect the rate of SN1, but it would decrease SN2, would it not?
I think you're right there, unless it influenced it and made it go one over the other. So I think you're asking a really legitimate question, and you're also getting to a level of detail that I'm not going to push you guys on and expect you to be able to, get into the super finer points of that, because I think that's like extra layers and years of studying this to get to that level where. So I'm going to realize that you guys are going to have a kind of a superficial understanding of this at best. So I think it's a great question, and I think it'd be hard to take it much more in depth than that. All right, let me go back to this slide here. Now what we've done is made the nucleophile better by making it negative, but also we're increasing its basicity, so it's a super good base. That's why we get so much elimination down here. So we kind of have to understand that. And the last thing we hopefully will understand is we get more elimination product that's this and less of this. So let's talk about that for a second. If we're doing substitution, this O comes in where the Briard is. And it's almost like we want to, if it's... So anyway, it's a straight up replacement or substitution. But it's of elimination, we're either going to be attacking this H, let's call it carbon number 2. Let's arbitrarily count from the... Actually, we're going to have to call it carbon 3 because we should technically count from this side. So this H could go away. We could call it off carbon number 1. Or this H could go away off carbon number 3. This is saying we get more of this happening than this. Now, we know why this is. Let me just get you to remember what that is. Why is it that this H goes away more and this H less when we form these products? So see if you remember that, and then we're going to go to the answer, or we'll get Kira to maybe answer. It looks like your hand is up. Kira?
Doesn't it have to do with the rule that H's want to stay with H's we used like 2 or 3 units ago?
Almost.
Which one is that?
That would be the Markovnikov rule in terms of Yeah, so I think we're looking at a slightly different answer than that, though. Does anyone remember? Markovnikov. Peter?
It's Zaitsev's, right?
This is Zaitsev's rule that the more, what is it called? The more substituted alkene will form instead of the less substituted. So, but wait a minute. Is there a difference in them? I'm actually noticing there's no difference, is there?
There is a difference.
Yeah. Sorry, one's at the end. It's got 2 hydrogens, and it's only got so the 16% one, the one on the right, is only got a carbon on each side. But this one's actually got 3 carbons, one on the right, one here, and then one popping off. Sorry, yeah. So it's the more substituted. This is a Zaitsev product. All right. Good. All right.
Mr. Walker.
All right. Yeah. Question, Peter. Thank you.
Yeah. Sorry. On the last slide. Is why isn't E1 formed in that?
Let me see if I can answer that. E1 would have to be the bromine leaves and forms a carbocation, and yeah, I'm not sure I have a good answer for that. Because I don't see, it seems like to me it's caught in the middle there, and this is where I wonder if maybe saying that they're all E2 products is totally correct there, Peter. So you've asked a question I can't fully answer. I don't have a good answer to it.
So
I apologize.
Do you just want us to memorize what different things lead to?
Yeah, and I don't think, I wouldn't ask you whether this would lead to E2 or E1. I don't think that's a fair question, honestly. I think it would be more fair if this were a primary or tertiary, because then there's a likelihood that one happens versus the other. With a secondary like this, I don't feel it's a fair question, and I think it's too confusing and complicated. So I almost wish we didn't have this E2 written there, honestly. I wrote it there because the book did, but I think it's a little complex. So it's a great question. I can't answer that very well myself. Maxwell?
On Maximilian.
Maximilian.
On the test, will we be told, like,
I will try
strong
to be
base,
super,
like,
well,
because I mean, like, I know the negative, but like the negatives kind of give. Will we be told, like, strong base, obviously we won't say it pushes towards one, but will we be told anything about the?
Look at the test from last year, and I'll try to be very similar there. So I will try to lead you as much as I possibly can without giving away answers. I feel like I may have to expect you to know that that's a strong base. So I think we should expect that we know that's a strong base. Because it really wants that hydrogen back just to turn in a nice, stable ethanol.
We can just assume any negative is going to go E2. Or E, not E2. And push towards
Walker, is it alright if I go to the bathroom real quick?
Yes, of course. The only reason I wouldn't say, not to you, Keith, but the only reason I wouldn't say any negative, because the sulfur negative there is a great nucleophile and would push a lot of substitution. So I'm hesitant to say that. All right, so let's try this problem from our book, 7.4. Which of the following two methods for preparing this thing will give the better yield? So what they do is two carbons and then an oxygen negative, or do we have the carbons lined up, like carbon here, and then the oxygen and carbon? So basically, those are your choices. Also look at your leaving group. If your leaving group leaves here, you've got, if it's going to go a certain way, you'd form a cation with a primary, where if it leaves here, you've got a secondary. So again, you're going to form the exact same product. They look exactly the same because they are. Your question is, which reagents do you use to get a better yield? This is a great question, and you want to try to break it down and think it over a little bit, and then we'll go over an answer. And again, you've seen this in the video and had a little time to think about it, so we're not going to take too much time on this. But I do think it's good for your brain to think it through. Which will you think is the right answer? And here it turns out the second answer is the one that would go better, because if this bromine leaves, it's on a primary, it would form a primary carbocation. It's more likely to do substitution, and we want substitution. We don't want elimination, and so it's a better method. The first reaction would form a secondary carbocation. If this guy left, this carbon is sitting in the middle. There's a carbon up and down, if you will, these two guys. And, there's much more possibility of some substitution, some elimination, and we want to go, if the goal is as much substitution product as possible, we want to go this route. So this is a well-formulated question. You may want to make sure you understand it, because, again, it's the kind of thing I would feel okay asking you on a test, giving you two options. And given the difficulty of this test, I'm more likely to go towards things you've seen before. And in other words, problems on the test might look like things you've either seen in the class videos or that are assigned for homework, and I'm going to stray less into things that are super difficult. So I plan to make the test look a lot like the problems you've already seen before and that you've seen on that you've had for homework. All right, here's another good one. The amount of elimination from one bromodecane. Again, you want to think, all right, I got 10 carbons and there's a bromine sitting on carbon number 1. With an alkoxide in the corresponding alcohol solvent is only about 1% for methoxide, so that's just with a single carbon. But for tert-butyl, in other words, you got 3 carbons coming off a single carbon, is 85%. Why do we get so much more elimination with the tert-butyl? And Margaret, you're super fast at drawing. Maybe you can draw us a carbon with a carbon coming off of it. Say again? Oh, I didn't make any of your presenter. I screwed up today. I was doing. So think about that for a second while I make people presenters real quickly, and we'll go over and answer in just a second. Sorry, I fell asleep on making presenters. I think I was so focused on getting class started on time.
So focused on Young Hyun not falling asleep, you fell asleep.
Are
we gonna make weight today, Young Hyun?
I quit wrestling.
All right, so I'm going to go ahead and advance, or I was going to try to, but apparently they shut me down on the... All right, here we go. So here's what methoxide looks like. It's just a single carbon, and here's what tert-butyl, it's going to have 3 carbons coming up, there, and there. Big and bulky, and so it's super hard to do SN2 if it's big and bulky. And you'd expect SN2 because it's a primary carbon, and so it should be easy for the group to come in and make the substitution and invert there. Also, this is a slightly stronger base, and elimination is a little more likely if you've got a strong base, a little bit stronger base. Just a little bit there. All right, so anyway, that's that one. And now we're into homework. So have you guys tried some homework problems that you'd want to do, and I want to do some, so ask me questions. Or otherwise, I'm just going to jump into doing some with you real quickly. 3, 2, 1. Okay, Mr. Walker, go. All right, I want to do 7.7 together. It's one that I wanted to do a while back, and then we kind of ran out of time. Look at 7.7. It's a great question, and it's got a little bit of a trick to it, and I want you to see the trick now and not surprise you later if you were to see a problem like this in the future. Let's read it together. Alcohols are converted to alkoxides by the reaction with sodium hydride. Treatment of the following compound with sodium hydride yields, something with a formula C4H8O. What's the structure of the product and how is it formed? Well, notice that we've got a bromine sitting out here, and what do we typically think of a bromine as being? A good blanking agent. Blanking agent, what kind? You said it.
Oh.
Leaving group, or a good leaving group. I shouldn't have said agent, leaving group. And
Producing agent.
yeah, I know, right? We've got an OH over here, and we're reacting the sodium hydride with it. Notice that the sodium hydride, they basically tell us it's going to rip the hydrogen off right here because it's going to convert the alcohol into an alkoxide. So this H is going to go away. And imagine that instead of an H there, I'm going to kind of cover it up with my pen or my pointer, we have an O minus sitting out here. And then you've got your bromine that's wanting to go away, or as a leaving group, and we know it does. Think about what's going to happen with an O minus with a leaving group. And this is kind of crazy because I don't think you've ever seen anything like this before. Yeah, watch what Margaret's doing. Do it again, Margaret. Look at what she's doing. So what does that mean? Do it one more time. The molecule does what she's doing. Oh, you can't see what she's doing? I'll do what she's doing. She's doing like this. So the molecule does, and she's doing this motion. Now look at the molecule. Imagine it. What would it look like if the bromine left and... a
ring.
Yeah, it'll form, say it louder.
A ring?
It'll form a ring. And the oxygen will kind of come along and bite the tail, if you will. Imagine it's like a snake. Come over here and bite this over here, and you'll form a ring, and it'll have 1, 2, 3, 4 carbons and an oxygen. Good luck at your game. You have a game?
Yeah.
Who are we playing?
Bishop Sullivan Catholic.
You going there?
No.
Oh, they're coming. Oh, St. Stephen. Good luck. Oh, good. Thank you for forming that. 1, 2, 3, 4. Yeah. Nice. Well done. Thank you. And this is what we end up forming. So this thing kind of like forms a compound and bites its own tail. As the bromine leaves, the oxygen comes in and forms a ring. Isn't that clever?
I know how to remember this one.
How do you remember this?
Oh, Ouroboros, because it bites its own tail.
Oh, Ouroboros. Okay, good. I'm just going to ask you to quickly look at 7.8. We're not going to take the time to do it, but it's almost the identical question. Treatment of the following compound with sodium sulfide yields C4H8S. What's the structure of the product and how is it formed? So again, here you've got a sulfide, which is somehow going to sneak on, a chloride that's going to sneak off, and another chloride that's going to sneak off. So again, I think you can kind of visualize, once you've seen it once, how this thing could kind of reach around, grab itself, and kind of form a ring compound. We're not going to take a lot of time on that right now, but I wanted you to show you that because I think it's kind of cool. And I think it might be hard if you hadn't thought of that possibility before. But a molecule can actually react with itself if it's long enough. I know, right? All right, let's switch slides. Oh, sorry, this is an answer to... Oh, I've written up some answers to 5. Actually, let me backtrack and do 5 real quickly because Oh, you know what? You may want to look at 5 and try it and make sure you understand it. Actually, it's just asking you to basically do some substitutions, and I've got the answer there. And I'm not going to spend much time about it. And the book has them answered in the back, but I'm happy to spend time on that later if people want. I'm actually going to skip it for now. There's my answer to 7. And let's go to 9. Okay, so here's where we get a choice. And again, you need to take some time drawing out the molecules. Which compound of the following pairs reacts with sodium iodide faster by SN2? It's key that it's SN2. Iodide's going to come in and replace the bromine group. So take a second. Would it be faster with 1 bromobutane or 2 bromobutane? Ramsey? 1 bromobutane, why? Good. Yep, I'm going to advance to the next slide. It would go faster for the one.
We didn't hear what you said again. Right.
Steric hindrance for 2-bromobutane because it's a secondary carbon.
Nice. So the first one, which I'm pointing to on my answer here, is a primary carbon, and there's less steric hindrance there for it to go SN2. With the bromine in the middle leaving, there's more bulky stuff on the sides to get out of the way as you go SN2. Let's go back. Let's look at B now. B says, which would be faster SN2, 1-chloropentane or chlorocyclopentane? Again, without taking a lot of time, if you visualize those, which one would go faster SN2?
1-chloropentane.
Yes, and the reason is shown on this slide. Here again, we've got a primary, and it's less steric hindrance than for a secondary. So the entering group would have to come in and got all this ring structure in the way. Last one for 7. What if you had 2-bromo, 2-methylpentane, so your bromo group is on the same carbon as 2 other methyls, or 2-bromo, 4-methyl, where the branch is way down the ring or the chain? I'll just skip over. Here's the first one they said, and it's too big and bulky. It's a tertiary. The second one they said, or the second one they said, which is this one, would go faster because it's a secondary. It would be faster by SN2, and this would be the slowest. Again, I know we're going over this a little on the fast side, but again, in theory, you've looked at these at least once for homework, and if not, please do so.
Sorry, but was the drawing on the other one 2-bromo? Yeah, that's a butane.
Did I make a mistake? 1, 2, 3, 4. Yeah, I did do too many, didn't I? So what I need to do is...
No. The second one, it's supposed to be pentane, but...
Thank you. So I need another carbon. Thanks. I need another carbon right here, right?
Yeah.
Yeah. All right. Thanks for catching that mistake on my notes there. Let me actually correct that now so I don't perpetuate that error for long. This is question number 9. Thanks for catching my mistake. All right. Let's go on. Okay, so, let me backtrack 1 second. I think 710 is a good problem, even though I didn't assign it. I'd encourage people to look at it, and I plan to try to look at it with you in the next class. Because in the next class, I want to spend a lot of time going over these end-of-the-chapter problems so that you feel really confident, I hope. So I'd like to look at 710 in the next class. I won't today. 711. Oh, give me a Slurpee. Sorry, I couldn't resist. Let's look at 711. Predict which compound in each of the following pairs reacts with methanol. Ooh, methanol. Is that a good or a bad? I can't move my cursor. Why won't you move, pen? Can someone help me move that and point to methanol? Yeah. All right. Methanol, is that a good nucleophile or not so good nucleophile, people?
Bad.
Yeah, not so good. Which of the following compounds will react with methanol faster by SN1? Remember, SN1 is where we got to pop that leaving group off, and then the methanol's got to come in. Would it be better to have bromocyclohexane or 1-bromomethylcyclohexane? And again, you have to take time to draw these, so I'm going to advance to the next slide just kind of quickly to help us a little bit. Look at the 2 structures. Here is the first one they mentioned. Again, I'm having trouble moving there. Here's the first one they mentioned. Here's the second one they mentioned. If the bromine pops off, which of these is more stable? Which one?
Second.
Yeah, the second one, because it's a tertiary carbocation. This one's only a secondary. This is a great test question. Your book asks some really good questions. This is just an example of a really good question. All right, let's try B. Same kind of thing. Isopropyl iodide, the only thing I don't like about it is they're using common naming there. I don't like that. I'd rather them give the proper name, or isobutyl iodide. So I'm going to go to these where I've done them out. Here's the isopropyl. Here's the isobutyl. This is a secondary carbon right here, and this would only be a primary carbon once the iodine left. Secondary carbocation is much more stable and more likely to go SN1. And then finally for C, would it be better to have 3-bromo-1 pentene or 4-bromo-1 pentene? This one's kind of tricky because it's got an E in there, and I hate to advance to the answer, but I do want to kind of get to this kind of quickly. If you draw it out, here's your double bond and here's your double bond. Notice where your leaving group is, notice where your leaving group is. If it pops off here, we get a plus right here, and notice, bam, we can have resonance stabilization. If the bromine pops off here, we can only stabilize if it were right here, and that won't happen. We can't stabilize 2 over. This is resonance stabilized, much more likely to occur by SN1 than this one. Again, the book just asked 3 beautiful questions right there. I love them and would be thinking I'd love to ask a question just like that on the test. Woo-hoo. And I'm betting that 712 is very much similar to it, and would be another good kind of question to ask. Keeping an eye on my clock, I got about 6 minutes, so trying to make effective use of time. Let's go to 713. Para-methyl benzyl bromide reacts faster than para-nitrobenzyl bromide with ethanol. Again, ethanol is not a great, man, I can't point anymore. Somebody help me grab the pointer and move it. Thank you. I don't know why it sometimes gets locked. Thank you. So ethanol, I got it now. Ethanol is not a great nucleophile, and it's a really horrible base, but to form an ether product suggests a reaction, a reason for this. So para-methylbenzyl goes faster. Let's look at what that looks like. Here's para, opposite one another. Here's a methyl group versus a nitro group. Try to not look at my answer. You know, what would be better about having a methyl group there than having a nitro group there if we're going to rip off a bromine? All right, so if we think about that for a second, we've got a positive charge build up as soon as the bromine leaves. A methyl group, does it tend to donate electrons into the ring or suck them out? And a nitro group, does it tend to donate electrons into the ring or suck them out? What's the answer to those? I've called on Ramsey a couple times, so I'm going to call on someone else. Anybody want to try to address that for the methyl or the nitro group in terms of donating?
Can you just repeat that one more time, like the whole question?
Yeah, sure. The nitro group is either, the nitro group, I'll point to it, is either donating electrons or sucking them in, out, thank you. Or the methyl group here is either donating electrons in the ring or sucking them out. Which is going on? Peter?
The methyl is donating.
Donating, an R group donates, and that's actually going to help stabilize a positive charge, whereas a nitro group does the opposite. It sucks electron density out, and that's going to make a positive less stable. So that's why this one on the left goes faster. Again, this is a complicated and more difficult question, but I appreciate it, and I think it's a well-asked question, and I hope the answer makes sense with a little thought. All right, so again, let me just backtrack. 712 is one that I didn't assign for homework, but next week I'd actually like to go over it. So I've got an answer actually that I'm prepared to go over with you guys. Let's go to one that was assigned, 715. This is a tough one. The structure of the product, write the structure of the product of the reaction of R, again this is R as opposed to S, 2-bromobutane with sodium cyanide. Let's just take a second and talk about what's going to happen. What's cyanide going to do in terms of this compound? Can someone just give me a hint as what you think cyanide would do? Yeah, Ramsey?
It's going to rip off a hydrogen, one carbon over from
It could do that. It could act as a base to do that, or it could do, what's the other possibility? That's elimination. What's the other possibility? It could substitute for the bromine. And it turns out that's actually what's going to happen in this compound, and we'd have to maybe look at the product to see. Let's go to the slide and look at what we start with this thing. Notice that it's a secondary, so you actually have to kind of draw it out to make it make any sense, and you have to prioritize the groups. So I have 1 here, 2 here, 3 here, and I drew it so that if I go like this, I'm going in a clockwise direction, and that's R. Notice that it's a secondary, and here's how tricky this can get, though. Cyanide is a really, really, really good nucleophile. It's negative, big, and squishy, and it's going to help promote SN2. The question almost is hinting at you for that because it starts off as R, And what happens is the entering group comes in, the nucleophile comes in on this side, the leaving group leaves on this side, and it inverts the geometry. So the answer is we end up forming S, the S product. Now again, this is super tricky, and I can see how Ramsey would want to say, this thing acts as a base and does what he said, but it turns out it's actually a better nucleophile than a base. And this is going to take a little practice. And again, you may want to just write down that cyanide and like that big sulfur minus is just a super good nucleophile, and if you see it, suspect substitution. And so again, this is kind of tricky. And take a little moment to look at that a little bit more. Let's look at 17. Write the structure of the product where here we're going to have another R, but this time it's a 1-phenyl, 1-bromobutane. Oh, and look what we're reacting with, water. Do you think of water as being a good nucleophile or a bad nucleophile? Neutral water. What do we think? Bad nucleophile. Not a good nucleophile at all. And if you're not a good nucleophile and you're going to do substitution, because water's a horrible base, it's not going to cause elimination. So we're going to do substitution. If you're a horrible nucleophile, which mechanism are you more likely to go, SN2 or SN1? SN1, and in SN1 the leaving group leaves, so that's the bromo group leaving, and water's going to come in. Now what's the entering group if it's water? Remember, you don't want to think of it as H2O, you want to think of it as what? What's going to go away? The H is going to go away, and think about an OH coming in. So it's going to be able to enter, and since it's a carbocation, it can enter from either side once the bromine leaves. So you'll form an alcohol, but will you make R or S or a mixture of the two?
Mixture.
You will actually form a mixture. Now I realize a question like this is difficult, and I know it's hard to keep track, but here are the hints. So here's what this would look like. I didn't even draw it out because R didn't matter that much. But we know that it's also going to be a resonance stabilized carbocation because it's right here on the benzene ring like this. So when this goes, it's almost definitely going to go SN1. Water is protic. It's going to screw up. It's a weak nucleophile. It's not going to go SN2. And with the bromine gone, the OH can come in on either side, and it'll form a mixture of R and S. I'm out of time. I ran over by 1 minute. I will see you guys. We will have class on Monday. Please do as much homework as you can. Do all the homework that's assigned and maybe even some of the even ones, and try the practice test so when you come into class on Monday, you're like, man, I finally am starting to get this stuff. Even though it's difficult, I got it, and I'm going to do well. And that's the best. All right, guys, have a good weekend.
Yeah.
Take care. Take care. See you guys. Please do lots of your homework and be ready for class on Monday.
See you, Mr. Walker.
Don't forget to end the meeting. Extra credit for saying that.
Micro points.
End the meeting, please, in whatever language necessary.
Yes, Kira. Good job. Thank you.
Thank you very much, Mr. Walker.
Thanks, Robin. Have a good night. Man, this stuff is hard.
I thought cyanide is a pretty good base as well. Or is it a better nucleophile than it is a base?
It's not a horrible base, but it forms the weak acid HSCN. So since that's a weak acid, the base is not that kick. It's not that kicker.
Actually, I thought weak acids were strong bases generally.
But it's kind of like it's one of those like. Think about ethanol is a horrible acid, so it forms an incredibly strong base as the protons go.
In the middle, so
it's more like in the middle. It's not strong enough to rip off.
It's like a mediocre.
Mediocre acid. It's a wimpy acid.
Thanks, Mr. Walker.
See you. Good luck getting caught up on sleep. What do you do at night?
Work, because I get home late.
Yeah, from wrestling and stuff.
I quit wrestling recently, so
you?
I'm gonna have more time to sleep.
All right.
Because I had commitments and my coach was strict this year because we had a bad start to the season. So he said he's not letting me wrestle on his team because I can't commit 100%. So
Okay.
yeah.
Well,
Thanks, Mr. Walker.
Understood. All right, take care. How you doing, Ramsey?
I'm pretty good.
Good.
How are you doing?
I'm pretty well.
So should we do most of the unassigned, the odd number of unassigned problems? Do you think?
Do the odds that I've assigned, and then if you have time, it'd be great to do some of the evens just so you feel like you get a little extra practice, and maybe try that practice test. That would be the.
preference if we take it Tuesday or Wednesday?
No, I don't. I'm fine with anything. I know your schedules are complicated, so.
Would you mind Wednesday? Because I've got a math.
No, I know. I think you guys have a rough. You're fine doing anything with me.
Oh, actually, yeah, Monday wouldn't have worked anyway because I've got 2 assessments. Anyway.
Yeah. See, I think Monday was just bad.
Okay.
This is a hard week.
Thanks very much.
Yeah, you're welcome. And for my exam, does taking it Tuesday probably make sense? Because you'd have math on Monday, then physics takes priority, and Tuesday.
Yeah, Tuesday.
Math is Tuesday, physics is Thursday, so that's Orgo had to bump to the conflict period on Monday.
So it'll be in the afternoon Wednesday?
It's morning Wednesday.
Morning Wednesday.
You want to hit the lights when you leave?
Yeah, I'll go. Take care.
It always smells like
I'm really glad Sarah got into Indiana.
Yeah, seriously.
Do you have like a top school?
My top school, I think, is one that I will not get into.
Yeah, the same with mine. I have like a top school that I would really like to get in. Like I know I'm not gonna get in there, so I'm so.
And like, if I did get in, I would go there.
Yeah.
But
then I also have a top school that like I actually have a chance of achieving.
see, I don't even know if I have that. Like, I actually know that I don't have that because I was thinking about the ones I like. Was looking at the ones that I would most likely like get, like the ones that like I think that I would most likely get into. It's like, don't really like them. I mean, like, I like them, but I don't. It's not like I would be like, oh, ecstatic and over the moon. But then the other thing is I don't know them very well.
Yeah.
So. Like, one of them is one of the. I don't know. Hopefully a miracle happens and I get into one of the reach schools that I have.
I was thinking about it. I was like, oh my gosh, they could accept me, but then I was like thinking about it some more, and I was like, I don't know why they would accept me over like other people. Like, I got really sad.
Okay, I'm gonna go. I have to list out what I have to do first.
Wait, do you want to watch the video real quick?
Oh yeah, where is it?
Yeah, just Google it. It's like probably all over the web.
It's on YouTube. I'm just going to YouTube. Okay. Okay, what's it? Eric. Ugh, crap. Eric Gardner. Video. Okay.
This guy right here is forcibly trying to lock somebody up for breaking up a fight.
Everybody standing there, they told I didn't do nothing. I did not sell nothing. Because every time you see me, you want to harass me, you want to stop me, you want to talk. I'm minding my business, officer. I'm minding my business. Please just leave me alone. I told you the last time, please leave me alone. Hold on. Don't touch me. You better touch me. Put your hand behind your back.
Are you selling that?
Once again, police beating up on people. Back up right here. Back up and get on that step. Okay, back up. All he did was break up a fight. And this is what happens for breaking up a fight. This shit is crazy. Everybody back up, back up. Can't breathe. Look, now I mean, they gave this man a seizure.
No, move out the way. No.
It's my brother. We live here.
Back up this way. Everybody now back up. It's now going to become a crisis. Back it up. Back it up. Come on.
I'm going to my house.
This way. Let's go.
Can't go to my
In the house or that way?
All right, I'll go that way.
Pick a choice.
I'm getting my bike.
You had your chance to get your bike, sir. Staying over there. Right now we have to see it.
The video shows Eric Garner talking to officers, pleading his case. Police say the 43-year-old Staten Island man was selling untaxed cigarettes. Just 2 months ago, Garner was arrested for a similar crime. But this time, he was adamant, non-compliant but not aggressive, demanding he be left alone. The video goes on to show officers wrestling Garner to the ground, the officer on his back, placing one arm around Garner's neck to subdue him. Police Commissioner Bratton called this maneuver a chokehold. Garner, who weighs more than 300 pounds and stands well over 6 feet tall, repeatedly tells police he could not breathe.
After he was telling him, I can't breathe, he just went limp.
This woman, who identified herself as Garner's first cousin, said her loved one was not an aggressive person.
He wasn't a violent person. He was not at all.
Police say Garner went into cardiac arrest as he was being placed into custody. Less than 24 hours after his death, the area near Victory Boulevard and Bay Street became a rallying point for many in the community as they demanded justice. Meanwhile, in Manhattan,
like so many New Yorkers, I was very troubled by the video I reviewed earlier today.
Mayor de Blasio and Commissioner Bratton stood side by side, vowing a thorough investigation will be done.
It's too early to jump to any conclusions about this case. We must wait for all the facts and details of the incident to emerge. But I assure all New Yorkers there will be a full and thorough investigation.
About 20 to 30 people have been gathered here at Garner's makeshift memorial.
What? You found it?
Yeah.
Where was it?
On the floor. Under couch. I don't know how it got there, but okay. What did you think of the video?
I don't even know. It's funny because the way that my mom had described it was that she was like, I don't even think she had seen the video. I think she was just going off of what people had said. And she was just like, I mean, he was resisting arrest or whatever, and I was like, but like in the video he's not even really, he's just saying like leave me alone, and then like 5 of them just like, I mean he is I'm doing civil liberties in the news tomorrow, so it's when like one of us presents what's been going on in the news.
You're gonna present this?
Yeah.
Hi. Hello. Are you just hanging out studying?
Yes. Do you have something?
I don't have a class, but I do need to use the system. You're welcome to stay and listen if I can share your room.
I mean, we can leave.
Yeah.
We're just doing an Adobe Connect training session.
Oh. I mean, we can just leave.
Yeah.
If it's probably gonna. Yeah.
You sure?
Yeah. Because if you like watch a video or something, it would get
louder.
Yeah. Okay. Well,
I didn't mean to run you off.
No, not a problem. Bye.
Have a great day.
You too.